Okay, this video here is about the increasing and decreasing functions, so really about the rise and the fall of functions and how they oscillate, and then also a very important test for finding the high points and low points of functions. And this here we call the first derivative test. So most people have some intuition about increasing and decreasing functions that are rising from left to right and then also falling from left to right. So the first thing I'm going to do is just briefly talk about increasing and decreasing functions. So we're going to start off with this basic assumption for most of the examples that we're going to see in this section. So the function here has to be continuous and then also differentiable. So remember, graphically that means no gaps in the graph and then also nice and smooth. And we're talking about a function on the window from A to B. So here's a basic statement that captures everything that goes right into what we're going to call the first derivative test. So this looks like there's a lot of information here, but really if you understand one of these statements, you can almost infer the other ones. So the first statement here says, if the derivative is greater than 0, right, so if we have a positive slope for all x values in a certain interval, then that means the function must be increasing on that interval, so rising from left to right. So if we stop for a minute and think about what this first statement means, we could draw a little picture of a function. So here are the axes here, and I'm going to draw a little function like this. We'll call this f. And again, just look at the statement. It says the slope of the tangent line is positive. So if you draw a couple of tangent lines to this graph, and I'll put them in a couple of different locations. Say put a tangent line here, and then also maybe a tangent line here. So you can see the tangent lines here, the slope, f prime, is positive. And so what the statement is saying is it's giving you a statement or a clarification about the blue function, saying if the slope is positive, then that means the function must be rising from left to right. So you can think about the opposite of the statement, that if the slope is negative, then that means the function must be dropping on that interval. And then finally, if the slope is equal to 0, the function isn't changing at all, right? It's constant on that window. So naturally, most examples that we're going to see do not really fall into one category. There are many functions that we can see that rise for a little while and then they fall, right? And that's going to lead right to finding mins and maxes of functions. So in order to understand the definitions of increasing and decreasing, it's really helpful just to sketch a little picture and just look at the slope, right, whether it's positive or negative, and you can see if the function is rising or falling. Alright, so this is going to lead directly into the main result of this section, and that's this thing here. So this is called the first derivative test. I'm going to abbreviate it FDT, and what it's going to do is it uses the information about increase and decrease and lets you find the extreme values of the function. So anything in mathematics, you're going to have some assumptions. So I'm going to flash these up here really fast, but then really take this one down. So the assumptions of the first derivative test, we have to have a critical number of the function, and also the function has to be smooth on an interval that contains the critical number, but it may or may not be smooth at that point, right? So this could be a sharp point. So the important thing is this here is not the first derivative test. It's just telling us that we're dealing with a critical number, and it may or may not be smooth at that location. So now I'm going to put up the important information, because this one here, this is the statement of what is known in calculus as the first derivative test. So if we look at this statement, it's talking about a sign change in the derivative. So it says if the slope changes sign from negative to positive at the critical number, then that means if we look at the y value corresponding to that, that has to be a low point to the graph. Okay, just like many things that we see in math, once you see one statement, you can almost invert some of the phrases and you're going to have the other statement. So now if the derivative changes sign from positive to negative, it's just the opposite of what what's up here at that critical number, then you're going to have the opposite extreme value. So you're not going to have a minimum, but you're going to have a maximum. So what I'd like to do here is to take just one of these statements, talk about it in detail to see why. This is more or less something that you really don't have to memorize. You can just think about what the statement means. So I'll put this over here, and why don't we just look at the second statement. Okay, so we'll glance at number 2. So this is saying the slope changes sign from positive to negative, and that means we must have a maximum point. So I'm going to draw a picture here. Let's look at a function. So I'll draw the picture like this, like a little hill. And this is our critical number c. So remember, the earlier assumption is that we have to have a critical number at this location. So if you go up here, notice that the tangent line is horizontal. So it does appear to be the case here. F prime of c is equal to 0. So c is certainly a critical number of this function. So the key in understanding this is noticing the way the sign is going to change. So it says the derivative changes sign from positive to negative. So if you look to the left of the critical number and you draw a tangent line, so right about like this, you can see that the tangent line here has a positive slope. So f prime, right, is greater than 0. So you can think about this as just having a positive slope. And then as soon as you pass the critical number, the tangent line changes in its orientation, right? So the tangent line looks this way. So now f prime is less than 0, right? The slope is negative. So if you think about what this means, if the sign changes from positive to negative, you can visibly see in the graph, right, that means we must have passed in between the sign change a high point to the function, a relative maximum, and that is something you can certainly see in the graphic. So the idea of the way that these are changing sign, you can always back it up with a picture. So I'll leave to you guys, you could almost make the exact opposite picture, right, a reflection about the x-axis, and you would get confirmation of this top statement right here. So the basic idea behind the first derivative test is all we care about is how the sign changes, right, at a critical number, and then that way you can classify the extreme values. Okay, so we're going to finish things up just by looking at an actual example. We'll go through the work and then use FDT, right, the first derivative test. So this problem is saying let's find the extreme values, right, the high points and the low points of this function. This should be a fairly simple one because it is a polynomial, and we're going to do that via the sign change in the derivative. So what I'd also like to do in this example, even though it's not requested, we can write down where the function is rising and falling, so we get all of that information about the function. So I'll write down h here. Right, so a pretty nice function. So what we're going to do is to first locate the critical numbers. So we're going to find h prime. So this should be fairly routine. So we'll have 3x squared by the power rule, and then we're going to have the 2's cancel here, so minus 3x. Right, so the derivative is nice and simple, and because it's a polynomial, we know it's not going to have any sharp turns or cusps, so we're just going to have possible horizontal tangent lines. So I'm going to set this equal to 0 here, and what this is going to allow us to do is to dig up the critical numbers. So we can factor this here, pull out a 3x, and so I'll do that. And that will leave us with x minus 1, and that is equal to 0. So the only two numbers here that are going to make this true, x equals 0 and also x equals 1, and so those would be our two c values. So I'll write them up here, x is 0, and then also 1. So these are the critical x. So our critical numbers, so we'll kind of hold on to those. So according to the first derivative test, all we have to do is to check away from the critical numbers and notice the sign change, and then we'll have all the important information that we need to solve the problem. So typically the way I approach this type of problem is I'll put a number line up here, like this. And what we're doing is we're looking at the sign of the derivative. So I'll label the number line with the derivative. And we already know that we're going to have these critical numbers. So these numbers are going to divide the number line. So I'm going to put 0 and 1. The important thing is to put these sequentially in the correct order. And then all we care about is checking the sign of the derivative. And perhaps the simplest form of the derivative would be here. I'll just circle it, right? The factored variation of h prime. So I'll put this up here. So this is 3x times x minus 1. And so the way that we're going to do this is we're going to pick numbers in these three different regions, away from 0 and 1, and just observe the sign of h prime, and that will tell us if the function is rising or falling. So if you pick any negative number, right, any number in this region here, then that means this number will be negative, and then also x minus 1 will also be negative. So when you take a negative times a negative, that's going to give you a positive number. So what you could do is to put a positive sign here, and this is indicating that the function is increasing to the left of 0. So in between 0 and 1, you could pick a number like 1/2. So if you put 1/2 into this function here, this is going to be a positive number. A 1/2 in here, this will stay negative, and the product of these two will be negative. And then finally, anything to the right of the number 1, pick the number 5, for example, right? And this will be 15, and this will be 4. And 15 times 4, we don't care about what that computes to, we just care that 15 times 4 is a positive number. So all we do is we just check a number in each one of these regions, and we get the sign of the derivative. So I'll just put up our earlier note here that we were talking about, that this little sheet here, just the sign of the derivative is going to tell you whether the function is increasing or decreasing. So positive signs tell us that the function is rising, a negative sign tells us that the function is falling. And like most examples in mathematics, this function has a little bit of everything. It rises, and then it falls, and then it rises again. So with all this information, I think we have everything that we need. So we can jot down just some notes here. So where you see the positive signs, the function h is increasing. So I'll say h is, and we can say it's increasing to the left of 0. So from negative infinity to 0, and then also beyond 1. So from 1 to infinity. And then it is decreasing in this small little section here. So it's decreasing on the window from 0 to 1. So this just gives you the intervals of x, right, where the function is rising and falling. So some people, what they like to do is to draw a little picture that mimics exactly what this number line is saying. So you could say that the function is rising here, and then it falls, and then it rises. So as soon as you put a little diagram up like that, you could see that it's going to have a high point, and then it's also going to have a low point. So this is exactly the information from the first derivative test. So we're going to have a high point at 0, we're going to have a low point at 1. So that is good information to document. So I'm going to erase this down here. I need some room here. Okay, so we have a maximum at 0. This is going to be a relative max. So we'll say we have a maximum, and this occurs when x is equal to 0. So notice what we don't have yet is we don't have the y value of that. So I'm just going to leave that blank. And then we're going to have a low point here at 1. So this is a minimum that occurs at 1. So this is exactly that sign change, right? We go from positive to negative. That means we're going to have a maximum at 0. And then at this critical number 1, we go from negative to positive. So that means we have a low point there. So extreme values are actual points on the graph, so you need to plug these x's into the original function and just calculate them. So if 0 goes into h, this is going to give you a 2. And then if you put 1 in here, you have to calculate a little bit. 1 minus 1.5, and then add 2. So this is going to give you 1.5. So 3 halves. So there you have all the analytical information. You know where the function is rising and falling, and you have, you could basically say this cubic function has both a high point and a low point, right? These are relative extreme values. Alright, so final thing to do is, because this is all information about the function h, it is always a good idea to graph this cubic, right? Graph the original function and just verify some of the information here that we've collected. So here's a diagram of the graph. So this is really what the graph looks like. And so what you can see here, if you look at the actual shape of this, is the true shape of the graph in fact mimics the graph that we have here above the number line, and you can see the fact that it rises for a while and then it drops and then the function rises again. And notice the maximum at 0, 2 you can see right in the picture, so that occurs right at this location at 0, 2, and then there's a valley in the graph, a low point at 1, 1.5, and that is also fairly visible in the graph. So you can put a dot there to see it. So all of this information is verified. We're increasing here. There's a small area of decrease and then another area of increase. And the other thing that we can see from the first derivative test is that when you have a change in sign of the derivative or a change from increasing to decreasing, that will automatically speak to high points and low points to the graph.